Hello, today we're going to be doing lab number 4. So for today's lab, we're going to be using a multimeter to measure capacitance and calculate percent error. So the capacitance is the ability of a device to store energy by separating electric charges. So as I said, we're going to focus on the measurements. So first we'll find the plate area and measure the multimeter systematic error by separating the plates and recording all their readings. We'll subtract that error from all our measurements, then we'll compare our measured capacitance of the theoretical values at different plate distances. So for some important concepts to know, we have capacitance, which as I mentioned before, is a measure of how much electric energy a device can store by separating charges. Another one is systematic error, which is the built-in offset of the multimeter, and we find it by separating the plates and finding and recording all the readings that we get after that. And then the last concept I think is important to know is parallel plate capacitors. So that depends on the plate area and distance between the plates. So we'll compare our measured values to the theoretical capacitance at different distances, which is how we do the percent error. And that's how we'll do the percent error and be able to solve for all the tables for our data and analysis part of the lab.
Materials. Okay, so these are the materials that we're going to be using for this lab. In this lab, we're going to be using the ruler, we're going to be using the multimeter, and lastly, we're going to be using the parallel plate capacitor. Now, the first thing in the setup, for the setup, the first thing that we need to do to get the theoretical capacitance is get the area. In this case, we're just going to measure the radius of the circle. So we're just going to measure it, and we get 10, but that is in centimeters, so we need to convert it into meters, and once we divide it we get 0.1. Now we're gonna square that, and we're gonna multiply it by the pi, and we're gonna get 0.03141. Now we're gonna have to find the distance, which we just need to measure it like this, and we got 12.5, and that also is in centimeters, so we need to convert it into meters, and we're gonna get 0.125. Now the last thing that we need to do is divide these two and then multiply by the E0, which is 8.854 times 10 to the negative 12. And once we do that, we get the 2.225 times 10 to the negative 12.
For step 1, we are changing the distance of the two discs and reading the voltmeter and filling out this table.
For the second step, the first thing that we're going to need to do is get like the material and put it between the parallel plates. We're going to put it like that. So now we're going to measure the distance. In this case, it's going to be 0.3 centimeters, and we're going to convert it into meters, so we're going to get 0.003 meters. Now the second thing that we need to do is the corrected capacitance, and this one is basically just checking this, and for this one, for example, it's going to be 0.113. Now for the value of K, we're going to be using this formula, using the same area and the same E0 as the last one. The other part for step 2, we're going to be using the same thing, but in this case, we're going to be using copper. So we're going to put it in the middle of the parallel plates, there, and we're going to measure the distance. This one is 0.4, so it's going to be, we're going to convert the centimeters to meters, and it's going to be 0.004. Now, what we need to do to get the corrected capacitance is just check this thing, and it says that it's 0.084. And now, for the last part, we're going to be using this formula in order to find K. Again, we're going to be using the same area and the same A0. We need to put the two dialects in the middle of the plate, and we have to see if they're going to have a greater capacitance than 1 or than 2. We need to remember that 1, which is the cardboard, got a lot less than plastic. So for the two dialects, we got 0.071. So for step 3, we believe that if we put the both of them in the middle of the plates, we think that it's going to have a greater capacitance than this one, and it's going to have a greater capacitance than this one. And then for the third question, we think that it's going to have it's gonna increase our percentage error because we're gonna have a greater equivalent capacitance, so that's gonna increase the error. Next.
6. So in step 6, we're going to discuss our predictions and thoughts about step 3. So what we predicted was correct. This had a lot less capacitance than this one. And that's it. So for step 6, we found that this diode had less of a capacitance than this one. And for our percentage errors, we got around the same thing. And some of the reasons that may have happened is human error, because we measured wrong or because some of the steps that we did was wrong, and another was because of the theoretical values that we may have calculated or calculated incorrectly. So human error and theoretical value are the reasons that we got similar percent errors.
So for the data analysis part of this project, we started off getting the table by getting the area, the dielectric constant, and the systematic error. These are the values that we use for the rest of the tables. So for the table 2, we got the theoretical values using a formula and using the area, diametric constant. Systematic error, we used it when we talked about corrected capacitance. So this in table 2 is where we actually measured the experiment of the plate separation. We switched it to meters, so we had everything in the same units.
Whatever I need to get out of it.
So from the second table, we got the theoretical values that we're supposed to get from this amount of separation. This is in millimeters. When we turned to the table where we actually experimented, we converted it to meters so it'd be easier to do the calculations. These are the measured capacitance. This is what we got from when we measured the experiment. The corrected capacitance is this minus the systematic error. From this, we were able to get a percent error value. The percent error value is just the theoretical capacitance and the corrected capacitance. So if we see this, the measured capacitance goes down, the more the plates increase in length. Because the capacitance lowers, the further the distance of the plates. And as of the percent error, it gets higher with the distance of the plates. We can see we started off at 19%, and we ended up at 46%. So this is a great increase in percent error. For the table 3, we used the cardboard and the plastic, and we measured the distance between them. We used the corrected capacitance, which corrected against means that we used the systematic error, and from this we calculated a K value. Now this K value, we used it here. We calculated this using the corrected capacitance, and we calculated the equivalent capacitance using calculated constants. So this is the calculated constant, and we use this and the area to find this value. If we can see, they're almost the same value. After this, we put both the plastic and the cardboard in the experiment, and we used these to get the percent error. And the percent error was very similar because these two were very similar, but it's a very high percent error. We think this is due to human error or the other things we talked about in the video.
In conclusion, in this lab, we were able to use the multimeter to measure the capacitance of the parallel plate capacitor and compare those measurements to the theoretical values based on the plate area and plate separation. This gave us a clear understanding of how capacitance depends on the physical setup and how the multimeter reads those values in practice. By working through different plate distances, we saw how the capacitance changes and how closely our measurements follow the expected behavior of a parallel plate capacitor. Overall, in this lab, we helped reinforce how capacitance works and how to use a multimeter effectively and measure.
I'm Miriam Alvarez, and I did the procedure.
Hi, I'm Gabriela, and I did the data analysis in the tables.
I'm Excel, I helped with the procedure, and then I edited and then recorded the video. My name is Gabby, and I did the introduction for the lab.
My name is Alan, and I did the conclusion and part of the first procedure.